Hello everyone and welcome to today's webinar. Today's webinar is titled AnyBodyRun, a web application for running biomechanics. My name is Christopher Iversen and I work here at Anybody Technology. Today I will be the host of this webinar and I will be joined by my colleague Bjørn Keller Ingelund, who is also a R&D engineer here at Anybody Technology. Bjørn will join us during the Q&A session and help out with answering your questions. In today's webcast, our speaker is Professor John Rasmussen. John is the head of the Biomechanics Research Group at the Department of Mechanical and Manufacturing Engineering at Aalborg University here in Denmark. He's going to give his presentation in a minute or so, but just before we start, I will give you a general introduction and overview of the AnyBody modeling system, for those of you who is unfamiliar with the software or musculoskeletal modeling in general. So, what is the AnyBody modeling system? Well, the AnyBody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data as kinematics and forces, and it calculates internal body loads as joint moments, joint reaction forces, and muscle forces. And here in the bottom of the screen, you can see a screenshot from the AnyBody modeling software, which can give you an idea of how the system actually looks. At the moment, AnyBody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation, and assistive devices as, for example, an exoskeleton. The typical workflow in AnyBody could look something like this. So you provide the recorded motion data as input, and you use the body models which you or others have built, and then you provide some kind of environment which could be an exoskeleton. You can then use AnyBody to combine these things, solve the muscle recruitment and run the inverse dynamic simulations, which basically means that we go from motion to calculate the internal body loads and the interaction with the environment in some cases. We then get a simulation that looks something like this. And we can then output the results and use it for some kind of post-processing with, for example, some kind of finite element tool. But many users also closes the loop completely by doing some kind of design optimization and run this cycle multiple times. I think this brings me to the end of the introduction, and I will hand over the presenter role to John instead.
So thank you very much for showing up for this presentation. My name is John Rasmussen, and I am going to go through 3 parts of this presentation. So I will first give you a general introduction to the idea of performing statistical running analysis and what it can do for sports science, I hope. And I will dive a little bit more into the ideas and the technology behind it, and then I'll give you some perspectives on the future at the end. And the reason why we are having this webcast today is that we recently released the AnyBodyRun.com website, on which, and I guess the reason why most of you are here is because that you have been to that website and you have tried it out. If you haven't done so, I encourage you to go there and try it out. You can even do it while I'm speaking if you think I'm too boring. But the AnyBodyRun website is actually is a simplified implementation of something which is a little more complicated and has somewhat wider perspectives than what you can see on the website. And I'm going to try to convey some of those to you. Before I do so, I just want to give kudos to Christopher and Bjørn, who are not only the hosts of this event, but also were very instrumental in the actual implementation of the website. And I think they did a really good job. So with that, let us proceed to the introduction. And I want to begin by drawing out the general landscape of running, simulation, and all of the things that you can do. Perhaps I think very, very likely a lot of you or several of you are runners. Maybe you run you run for your own pleasure. Maybe you run to stay in shape. A lot of people are running. It's actually a rather large percentage of the population in Denmark and also in many other countries who run recreationally and have that as their sport. I think especially in these times when it's difficult to do any sort of team sports for obvious reasons, it's something that anyone can do. You just put on a pair of shoes and you go running. And with this enormous interest in running also comes a lot of new technologies that are influencing what you can do with running, and also a lot of companies that are filling out the landscape of providing stuff for runners. And you can see some of the names here: Garmin, Polar, Fitbit, Strava, and so on, are probably names that you know already if you're a runner. You can also see over here on the right-hand side, you can see some of the technologies or gadgets or whatever it is that you can get, and technologies that are influencing the whole landscape of what we're doing here. So it's general things like social networks and big data and so on. And it's also rather specific things for runners, like running watches or mobile technology and other wearable gadgets that you can put on yourself and which can give you some information about how you're running. And the way that works for most people is that you have some sort of wearable that you have on your body. In most cases, this would be a running watch, but it could actually also be your cell phone. And this wearable has some sensors that can detect various things. For instance, it can detect some properties of how you're moving through an inertial measurement unit sensor that is embedded in the device. So it can measure accelerations and it can measure angular velocities. It can possibly also measure your pulse, and it probably has a GPS device built into it so that it can see exactly where you are and how far you're moving while you're running. And all of this means that if you take the accelerations and the angular velocities and the GPS information and the pulse and so on, you can put that into some processing algorithms, either directly where you are in your watch or possibly in the cloud. And you can get back information about your running speed, the distance you covered, the number of running meters, height meters that you covered, the step frequency and the calorie consumption and things like that. So all of this is really wonderful information. And the question, of course, is what else could we possibly want in addition to this amazing technology that is already there? And so the answer to that, it comes here in the idea and technology section. And of course, when you're visiting Anybody Technology and Aalborg University's biomechanics department, we are going to talk about biomechanics, obviously. So if what we can do here is we have spent many years building biomechanical models and software to analyze them. And out of these models come muscle forces and joint reactions and the mechanical work and metabolism of single muscles in the body, all of them together or each of them separately if you want. Forces and tendons and ligaments, efficiency and things like that, which are tightly linked to the biomechanics. Now, so that would be pretty nice if we could get that out for if you and me and everybody who is a runner could get this information out whenever we go running. We could see all of these nice features about our bodies. Maybe we are getting injured. Maybe we want to reduce the load on specific structures that are starting to hurt, or maybe we want to improve our running efficiency. Maybe we want to figure out what kind of training, muscular training, could we do in order to improve our performance. There are many biomechanically related questions that we might ask. The only problem is that in order to make a model like this, you have to input a whole lot of data. And let's look a little bit closer on what they are. So the traditional way of making this type of model is by going to the lab and putting optical markers on a body. Those are the blue and the red dots that you see here. And then once we put them on, we use a motion capture system based on cameras in order to capture the trajectories through space of these markers. And then from that, we can reconstruct the detailed motion. We also need some anthropometry, and we probably also need some force platforms in the floor, which can measure how hard we're stepping on the floor, and thereby also the forces that are coming into the body from the floor. And if we have that, it's all fine and dandy. Then we can measure and we can do analysis and so on. The problem is that most people don't have that. So it's a long way from a running watch to a lab that is equipped to do something like this, and people are not going to have that. So we have to figure out if we want to make this technology available to the people, then we have to figure out how to avoid these things. And the first thing is easy to deal with. So the force platform input, we can actually do away with that. We have, I think, really convincing results that show that we can simulate what the ground reaction forces are quite accurately if we know what the motions are. Okay, so I'll get back to there's a publication about that. I'll get back to that in a second. So let's just say that thing has been solved. No problem there anymore. Then the second thing is the motion capture and the anthropometry input. Now, we don't have that if we haven't got a motion capture system, because the anthropometry actually also comes from the motion capture data in this case. So what we're going to propose is that instead of measuring this, we are going to try to use some of the new technologies that are coming out, machine learning, big data, neural networks, deep learning, all of this hyped technology that is coming out in these years, and which are exploiting large amounts of data in order to find specific information. I think that's the best way I can express it, that's what's going on. So we are going to try to see if we can get our hands on some big data, and then we will see if those big data can solve these problems for us. Can they provide the motion capture input and the anthropometry input? So that's what we're going to try to do. Now, I said I would do away with the ground reaction forces. There is a very nice paper by a colleague of mine, Sebastian Schelz, and also some other, I'm not a co-author on this, but some of my other colleagues are. And it's in multi-body system dynamics. You can look it up if you want. And that has shown that for a wide variety of different motions, you can actually, if you know the motion, you can predict the ground reaction forces quite accurately. And this came as somewhat of a surprise to us, because initially we didn't think that was possible. But it actually turns out that this can be done really accurately. So that's not the problem anymore. Now, let's turn then to the statistical data, and the best way I think I can ease the way we do this into you is to try to paint a picture in your head of a whole lot of people running, and this picture that we have here is going to help me doing that. So if you look at the picture, you can see that here's a whole lot of people running, and when I say a whole lot of people, it's because I'm absolutely sure that when you look at the picture, you can immediately recognize that there are people in the picture, even though the people are very different. Okay, so there are men and there are women, they have different statures and different body mass indices and so on. So they're all really different. They wear different colors of clothes and whatever, but you recognize that they are people, because even though they are different, they also have a lot of things in common, okay, which enable you to recognize immediately that here are people. If I asked you to count the number of people in the picture, you could do that quite accurately. I could say the same thing about the running style. Now, this is not an animation, this is just a still image. But if you imagine that we were standing next to this running event and we were looking at it, we would immediately see that all of these people are running in different ways. They all have different running styles. Not only the velocity, even though some will run much faster than others, but also just the styles. Some will have a heel strike, some will have a forefoot strike, some will have varos, valgus, different styles of moving the arms or whatever. There are so many different ways that you can run. So we will immediately recognize that there are differences, but you will also, and here's the point, you will also immediately recognize that all of these people are running. And how can you tell that they're all running? Well, because there are also a lot of similarities in running. So this fact that there are similarities between people and there are similarities in running that make us recognize that there are people running here. This, in mathematical terms, this means that the data that are describing what we are seeing in the picture are correlated, because there are patterns in these data which we recognize. For instance, the motion pattern of a person who is running And even though the motion pattern we see is a little bit different from what we're used to, we can still see the person is running. And that's the whole clue here. That's what we are after. So this means that if we record a lot of people running and we somehow store the data for people who are running, we are expecting that we can find strong correlations in that data set. And these correlations are what we are going to use in order to solve our problem. So let's see how it's done. The first thing we do is we need some data. And for that, we have a very nice collaboration with a running shop in Copenhagen in Denmark. The name of the company is called Kaisersport and Orthopedics, and they are running specialists. So if you're an enthusiastic runner and you want to have your running pattern analyzed, or if you have some sort of problem with your running style or injuries or whatever, you can go to this shop and you can get an analysis of your running pattern. And the way it works is that they will strap optical markers to your body, and they will put you on a treadmill and you will run, and they will record the running motion by means of a motion capture system. So, and they have a flow of people through this shop, and we have the permission to use the data that they collect. And of course, with all the GDPR, data protection, ethics, and all of that has all been taken care of. So what we can do here with the raw data is we get the marker trajectories. We can process them through AnyBody exactly the same way we have always done. And then we can get out in the other end, we can get joint angles. So we get joint angle variations. And they look, for instance, like this. And now you can see what I told you before, that there are similarities between the way people are running, because each of these curves represents one joint angle for one runner. And you can see that some of them are very similar, and also some of them are quite different. There's, some are similar, some are different. It's exactly what we expected. Now I just need to, I need an easy way to represent this. I need to shrink this down to a few numbers that I can deal with. And the way that I do this is that I take each of these curves. This is represented, each curve is represented by thousands of samples. And but I take this and I do a Fourier approximation of that. So Fourier expansion, maybe I think most of you probably have heard about the fast Fourier transform. So this is really a way of transforming data by means of sine and cosine functions. So what we have with running data is that it's cyclic. You repeat the same motion over and over again. So you know that the functions we're going to approximate are going to be cyclic. And sine and cosine functions are really, really good at approximating something which is cyclic. So that's what we do. And the question then only is, we know this is a convergent series. So we know that if we have enough terms, eventually we are going to get it right. We are going to have a really accurate approximation if we put enough terms into this expansion. So the question, of course, is how many terms do we need? And there's a very simple answer to that question. The answer is 6. So the number n here in my summation sign that is necessary in order to approximate this reasonably is 6. And we have recently published a paper that show that goes through all of this and looks at it in different ways and comes up with a number 6, by the way. It's in the Journal of Biomechanics. You can look it up if you're interested in the actual way that we do this processing. The result that comes out of this is that each of these curves, which, as I said, was thousands of samples, is now described by 6 terms in a Fourier expansion. And 6 terms actually means we have 11 numbers. I won't go into that, but 6 terms ends up with 11 numbers. So each curve I can describe with only 11 numbers. But it's still quite a lot, because I have 104 degrees of freedom in the musculoskeletal model. And I have 285 runners. And so if I multiply that, you can see that I get about 30,000 functions that I need to approximate. So that's a lot, of course, but we let the computer do it. It's not a big problem. And then we end up with a matrix that looks like this. It's much, much bigger than what you see here on the screen. And you're not supposed to look at the numbers or anything. It's just get the idea that this is a big matrix of data. Each row in the matrix is describing how one of our test subjects is running. And the row is also describing the anthropometry of that test subject. So it contains the whole thing, the human and the way the human is moving together in one row. And then we have 285 rows here. Each of the rows has about 1,400 columns, because that's how many parameters we end up with to describe one runner. And then if you're, if you know a little bit about statistics, you will immediately say, okay, so you have a 1,400 dimension space, and you have 285 points to approximate that. That doesn't actually seem like very much, and you would be completely right, that isn't very much. But what we do then is we subject this to a principal component analysis. And remember, I said before that we expect that a lot of these columns are going to be dependent of each other. They're going to be correlated. And the consequence of that is that when we do the principal component analysis, we will end up with a sorted amount of alternative parameters. And these alternative parameters are orthogonal, so we can vary them any way we want, and we can produce new running patterns that way. The question is then, how many do we need? And it turns out that we need about 40 if we want to represent about 90% of the variance in the data set. Then we need to include about 40 of the principal components. The rest of them don't actually mean much. The remaining 1,360 parameters, they don't actually amount to more than 10% of the total variation. So it's not very important that we sample that part of the space very much. So now we have 285 parameters to cover a space, 285 points in a 40-dimensional space. It's still not too much, and we will, of course, put more data in as time passes. But right now, it's actually enough to represent a lot of the variation in the way people are running. So what we have now is we have a parametric running model from which we can generate artificial runners. We can set these 40 parameters here at whatever values we want, because they are orthogonal. And then we will produce virtual runners whom, by the way, are running in realistic ways, because we're using the PCA components here to generate them. So what we get out of that is actually a new way of making biomechanical models. So the old way, like I said, with the lab and the motion capture and all of that, is that in the old days we would take subject-specific data, and we would then collect all of the data that were necessary to describe one subject, and we would then create a subject-specific model, and we could get some subject-specific results out of that. That's all fine, but it's really cumbersome to do. Now, what we can do instead with the new paradigm is that we start out by processing a whole lot of people. So that's our statistical or big data. And what that actually produces is a parametric model where we can vary the parameters. So the parametric model in principle is a model of everybody. It's a model of how any person is running. And what we do then is we then collect a little bit of person-specific data. And when I say a little bit, well, it could be the running speed, could be some simple anthropometry from the body that we are collecting. It could be something about, say, the landing, the foot strike style, other things that we might collect. Maybe a little bit about how the running watch is moving when you're running, and so that will give you something about your arm movement. These would be little data. We use them to put into the big data, and what they do is they seed the big data model so that instead of having models of everybody, we find the combination of parameters which will, as accurately as possible, create a running model that replicates the little data we have put in. And so that gives us a subject-specific model only by collecting little data. And so that's actually really nice. So we can do, for instance, if we set all of our principal components to 0, then it turns out we get the average runner. So that's the one you see here on the screen. And remember, this is not any particular person from the data set. This is a completely virtually generated model. there's no motion capture markers here because this model was never captured in a lab. This is a synthetic model that is generated by a machine learning algorithm. So it's completely virtual, but it's still completely detailed. It has all of the variations, all of the motions that the original body had. And now we can put that into the biomechanics software, and we can simulate all of those nice biomechanical properties that I talked about before. And we can even make this model prospective because it's so easy to generate new models. We can, if there's something we are thinking about changing, maybe the foot strike, then we just change it in the model, we run it again and see what happens. Okay, so I haven't got time in this webcast to go into all of the mathematics and so on how we do this, but there is a paper you can read if you're interested. It's an open access paper, and you can see the link here, and if you haven't got time to write it down, this presentation goes up on YouTube at some point in the next few days, and then you can always review it. But from this link, you can download the paper. You can see how all of the math stuff is done. So we have not quite arrived yet at the at AnyBodyRun.com because we're going to make a stop first at where AnyBodyRun.com actually comes from, and it comes from an implementation that we have made. We call it an app because this is programmed in a cross-platform development tool in Python, which is called Kiwi, and which actually allows you to write software that you can port to mobile devices as well. So this should, in principle, run on a mobile device as an app. I haven't actually tried it out, but it should do that. So right now it's running on my computer. And when you go into it, the first thing you see is this. This would be animated, so it would be running. You can see that it's running 10 kilometers an hour. You can see how much energy it's burning and so on. And you can also go to some submenus where you can see stuff about how, more data about this running process. And you can also set data about the running process. So you can set the running speed, you can set the foot strike pattern and so on. And then we get down here. I will just take my pointer. Oops, that was the wrong one. Pointer options. Where's my mouse? There. Okay, so down here in this section, you will find some output, some biomechanical output. Of course, the model produces much more output than this, but this is just what we put in as an example. And you can see that here are some of the data that you would be interested in if you were interested in injuries. In your propensity to get injuries from running. Actually, a lot of people get injured from running. And so we put in the patellar ligament force here, and we put in the Achilles tendon force here. And so the patellar ligament and the Achilles tendon are two places where runners tend to get repetitive load injuries. And then we could start say, what if we change the foot strike? What would happen then? And for instance, let's say that we were interested in let's say that this might be me running here, and let's say that I'm beginning to get knee pain. And one of my friends told me that if I change my foot strike pattern from heel strike to forefoot landing, then maybe then it's better for the knees, he says. Yeah. So, but I'm not really convinced about hearsay like that. I would like to have some hard evidence. So I go to the running app here. I take the slider bar here and I move it over there, and then I rerun it, and then I get this. You can see now the slider bar is moved over here, and you can also see the foot strike pattern here that now he's actually running on his forefoot. And what we get out of that is that now the patellar ligament force is 5.84 body weights. And what was it before? It was 6.37 body weights before. So it actually looks like my friend was right, that I can offload the knee a little bit if I run on my forefoot. At least that's what the biomechanical model says. But there's a downside to that, because if you look at the Achilles tendon force, that was 7.21 body weight before, and that will actually increase to 7.89. So if I'm beginning to get Achilles tendonitis, then this is probably not a good idea. I just repeat the findings here. You can see the blue one here is for the neutral or the heel strike running, and the orange one is for the forefoot foot strike pattern. So a little bit worse running economy. You spend a little bit more energy when you run on the forefoot, a little bit higher peak ground reaction forces. That might come as a surprise because people would say, well, it's kind of softer if you land on your forefoot. But actually, that's a deceptive idea to get because the maximum force in running is not at heel strike. The maximum force for almost all runners are in mid stance, and that becomes a little bit bigger when you run on the forefoot. You see the patellar ligament force will go down, the Achilles tendon force will go up, and we could make the same comparison for thousands of parameters in the biomechanical model if we wanted to. So now we are getting to the AnyBodyRun.com, because the AnyBodyRun.com is like an implementation of the running app that I just showed you, but for practical reasons, it cannot do all of the stuff that the running app can do. And the reason is that we have put in the implementation, we have put emphasis to the green thing that I have down here. So in the running, what we have put emphasis on is to have short computation time. And this means that if you go into the running app and you do something in there, if you change a parameter in the running app, you will get an instant response. You immediately see what's the result of what you have done. There's no computation time to wait for. So this instant response comes with some limitations. And the basic reason is that when we implemented the website, what we did was we pre-processed thousands and thousands of different parameter combinations. And then we had these pre-processed and we just stored them on the website. So there's a huge database on the website that contains all of the animations and all of the data that go with all of these many samples that we have done of our running space. And so when you pick a parameter, it will simply fetch in the database the one that you have picked, and it will bring it out. But the cost of that is all the orange parameters we have here. So we go from being able to have continuous parameters to only having discrete combinations. So you cannot set exactly the body size that you have because there are only some combinations available. We also go from having many parameters to just having a few parameters that you can set. The reason why that is necessary is because if we retain the many parameters, then the number of combinations will become astronomous and much more than we can pre-compute. And so that's not doable. And also the detailed output, we have only a few output variables in order to make the interface simple to do, simple to work with. So but let's look at the outlook. So I want to convey to you the perspective of this technology, and it is that maybe in the future, if we go back to the cycle, the data that you can collect with your running watch while you're running, it's still the same data. So it's accelerations, angular velocities, GPS, and pulse. Now we need to. This is our little data, and we need to put this into our running model in order to seed the running model to create a model exactly of you. And then it has to analyze that model, and that takes some time. And it cannot be done on your running watch or on your mobile phone because it's way too costly in terms of CPU requirements. So that would have to be done in the cloud. So the idea is that we can then take these acceleration, all of these data, we can put them into our database of runners in the cloud. We can look you up. We can seed the big data with your data, and then we can process them, and we can make an exact person-specific model of you. Not the stepwise parameters, but exactly your parameters. And then we might be able to give you back from this process some information on how to avoid injuries, how can you change your running pattern in order to improve your performance, for instance. Or let's say even in a longer term perspective, if we start changing the strengths of different muscles, how is that going to redistribute the forces in your body? And there's actually a potential in there. If you have some parts of your body that tend to get overloaded, then it's actually possible to modulate the loads on those parts by changing the distribution of muscle strength in your individual muscles. And questions like that could also be answered with the technology. So that's what we are hoping will happen sometime in the future. At least we are trying to do what we can to make it happen by creating this technology. And with that, I just want to thank you for your attention, and I would like to also say thank you to the biomechanics research group at Aalborg University. It's these fine people that you see here. I would like to say thank you to Anybody Technology for hosting the webcast, and also especially for implementing the technology into their software, and also on the AnyBodyRun.com website. Again, very good work, Christopher and John. Then I would like to thank Kaisersport and Orthopedics for making the data available, and also finally the funding sources, the Innovation Fund Denmark, which puts quite a bit of money into this. So with that, I give the word back to Christopher, and I think he will take your questions and do his magic with them. Thank you.
Yes, so thank you very much for the presentation, John. Yes, so just before we go to the Q&A session, I would like to say a few words regarding our online resources. And if you want to know more about Anybody Technology, you can go and check out our website, anybodytech.com, for events and special dates, and also a full publication list of studies using the Anybody modeling system. You can also go and check out anyscript.org, which is our community website for people using Anybody. And here you can find multiple online resources as our wiki page, several blog posts, and links to our repository sites. And it's also here you can find our forum, where you can go and ask questions and get some help from some fellow Anybody users. I would also like to point your attention to an upcoming webcast we have on the 23rd of March, which has the title "A Methodology to Evaluate the Effects of Kinematic Measurements Uncertainties on Knee Ligament Properties as Estimated from Laxity Measurements." And you can go to our website already and secure a seat for this. But you can also keep an eye on our social media sites, where we will also post the registration links. And then I would also like to mention that Aalborg University here in Denmark is planning a new advanced musculoskeletal modeling PhD course, and it's set to be held the 3rd to 7th of May. And I'm getting told that this will be an online event. And last but not least, if you have any questions or you want to meet up, or you are interested in having a trial version of the software, then please feel free to send us an email at sales@anybodytech.com. And if you have any follow-up questions regarding this webcast, then please feel free to send me an email at ki@anybodytech.com.